Let's take a look at how to take direct measurements in a lab. First off, there are two types of instruments that you will use. Analog instruments. Now, an analog instrument is where the reading is found by comparing something to tick marks. For example, a clock, right? There are little tick marks and hands that go, or a meter stick here, little tick marks, if you will, and then you look at where the object is at in comparison to those using your eyes, or maybe a graduated cylinder. Or a digital instrument. Now, a digital instrument is different. It provides a numerical readout of the measurement. There is no comparison using your eyes. You just simply read the number here. Now, in an analog instrument, you are allowed to measure down or to estimate to half of the smallest tick. So measurements are always going to end in the 0 and 5, and you'll see that in the next slide. On the other hand, in a digital instrument, whatever the reading is exactly what the reading is. There is no estimating another digit beyond. Uncertainty in an instrument is plus or minus the most precise digit of that measurement. Now, uncertainty is exactly like it sounds, how certain you are of the measurement. Of course, you're not perfectly certain. You can't be perfectly certain of anything whenever it comes to taking a measurement, so it's a range that the measurement could have legitimately fallen in. In an analog instrument, it will be half of the smallest tick, and with a digital instrument, it'll be plus or minus whatever the last decimal place is. Let's now look at this using a few examples. Let's start out by looking at length. I have here a cart that has rolled down a track or has gone across the table, some displacement, and we want to measure how far it's gone. We lined up the front of the cart with a 0, and then we let it roll. Now, on a meter stick, all the little tick marks are actually representing millimeters, and the numbers are centimeters. And there are 10 tick marks between them, thus millimeters, and I'm allowed, because it's an analog instrument, to measure down to half of the smallest tick. So now I'm going to take a look right here where the cart is actually aligned with the meter stick and get my measurement. Now I'm going to, looking at this, I'm going to say that it's closer to the 35.1, that's 1 millimeter mark, than it is to the halfway between, than it is to the halfway between the 5 centimeter mark and the 5.1 centimeter mark. Now, because of that, I would report this measurement is 35.10 centimeters, or 0.3510 meters. Why this last 0 is necessary? Well, first let's look at the first 3 digits. I have 30, I have 35, right here, and then after I have my 35, I actually notice that it comes to the 0.1 centimeters, or a single millimeter. But I have to remember, this is an analog instrument, meaning that I can measure down to half the smallest tick. So if I'm going to put my choices up above maybe and around this, this could have been half the smallest tick, 35.05. This also could have been 35.15, if you will. Half the smallest tick, meaning that it could have gone just before the 0.1, or it could have been just after the 0.1. Notice now I actually have something in the hundredths place, but I'm telling you, at least according to what I am seeing here, that it's actually closer to being right on the little tick mark, the 0.1 or 1 millimeter, than it is the halfway betweens. And I actually need to indicate that significant figures to whoever might read my measurement. So I'm going to write 35.01 to have the correct number of significant figures. Now let's look at uncertainty. Uncertainty of any analog instrument is plus or minus half the smallest tick. So let me open back up my circle there so I can get some uncertainty in this. So this will be plus or minus half of the smallest tick is, a millimeter, meaning that I'm able to go down to 0.05, that's half a millimeter. The millimeter would be in the ones place here, so 0.05 centimeters. All right, let's shrink that back and let's actually take a look at a couple of others. All right, let's actually look at 2 pictures here to get the length of a cart instead of just how far it goes. So actually trying to find the length of the cart. Whenever you're trying to find the length of something with a meter stick, it is best to not line it up with what would be the 0. Notice that the meter stick is a little beat up. So I can't say for certain that this is my 0 mark. So instead, I make sure to line it up with the 1 centimeter mark. And remember, I can measure down to half the smallest tick here. So this is actually a reading of 1.00 centimeters, and we'll give it some error here, plus or minus 0.05, but I'm going to do my best to make sure that it is perfectly lined up. Now, I'm going to measure where this side is and subtract to actually get the full length. Looking closely at this, I think this is closer to the halfway between these tick marks. So my measurement here, if this is the 20, this must be 12, 13, 14, 15, 16, 17. So I have 17 centimeters. Let's actually get rid of the centi part here for a second. 17 centimeters, point. Now this goes all the way over. 1, 2, 3, 4, 5, 6, 7. So I have a 0.7, and I think it's closer to the 0.75 than it is to the 0.70 or the 0.80. So 17.75 centimeters, once again, that would have an uncertainty of 0.05, giving me a final measurement for the length of this cart. Notice that we started the cart at 1 centimeter, went all the way to 17.75. So obviously I would have a final length of this cart of 16.75 centimeters plus or minus 0.05 centimeters. Always make sure that you measure down to half the smallest tick. And in a meter stick, you can measure down to half of a millimeter. Let's now take a look at how to measure volume. Now I have 3 graduated cylinders here, but it would be kind of tough to see what the measurements were if we were zoomed out this far, so I took some pictures a lot closer in. Let's look at this first one here. Now with graduated cylinders, what you have to realize is that the tick marks are not constant. You actually have to decide what each tick mark is worth first off. So here I can notice that I start at the 600, and then there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 tick marks to get up to the 700, which leads me to conclude that each of these goes up by 10 for each tick mark. So now taking a look at where this actual measurement is, right here, I can see that it's somewhere between 690 and 700 milliliters. Now, whenever you're measuring volume, you want to measure from what's called the bottom of the meniscus. Fluids, a lot of times in a graduated cylinder, will look like it has a slight thickness. This graduated cylinder is a little cloudy, so it's hard to see, but you might be able to see a shadow there. That would be the meniscus, or it'll look like it has a thickness to the surface there, and I want to measure from the bottom of that. So I'm going to say that this is closer to the halfway between of the 690 and the 700, right about in here, which is going to give me 695 milliliters plus or minus 5 milliliters, because I'm allowed to measure down to half the smallest tick. The smallest tick was 10, so it went up by tens each time, and then I measured and I said it was about halfway between, so between the 690 and the 700, 695, and the uncertainty with an analog instrument is always the most precise digit. That's half the smallest tick on an analog, so plus or minus 5 milliliters. All right, let's do 2 other graduated cylinders very quickly here. This one, the smallest tick, is different. This one, you'll notice, goes up by ones. I have 40, 41, 42, 43, 44, 45. Let's mark my 45 here, all the way up to 50. Measuring from the bottom of the meniscus, it looks to me like it's more on the 48 than it is halfway between, either above or below. So this would be 48.0. It could have been slightly above, 48.5, half the smallest tick, half of 1.5. It could have been slightly below, 47.5, but it looks to me like it's more right on 48, so 48.0 plus or minus 0.5 milliliters. Let's grab a third and final graduated cylinder here, kind of pull it over into some space. Now, once again, the tick marks are different here. I notice that I start down at 15 and make it all the way up to 20. And once again, there look like there are 10 tick marks between each one, meaning this is actually going to go up by 0.5. This one would be 16, here's 17, here's 18, here's 19, and here's 20. Now, since in this graduated cylinder it goes up by 0.5, half the smallest tick is 0.25 here. So I have a few choices. It's either on the 16.50, the O trying to indicate that it is exactly on the tick mark, or it's on the 16.75, halfway between the 16.50 and then the next tick, which would be 17. Looking at this from my perspective, this looks like it's closer to 16.75. So I would report this answer is 16.75 milliliters plus or minus 0.25 ml, 0.25 milliliters. Next, let's look at how to measure mass, specifically using a triple beam balance. So check this out for how to use a triple beam balance.
A triple beam balance is a great example of an analog instrument that has a very large precision. It actually measures down to the hundredths place of a gram. Start out with your triple beam balance by making sure it's zeroed out. Everything's set on your sliders at 0. Make sure that it's level here, and mine actually is right now. If it wasn't, there's a knob on this side. You can rotate clockwise and counterclockwise to make sure that it's all nice and level. Next, actually set the object on the pan that you're looking to get the mass of. Let's just get the mass of my stapler. Start out by sliding the largest slider forward, one notch at a time. And as you slide it, you can actually hear and feel an auditory click and feel it in your hands. Keep sliding over one notch at a time, making sure it's clicked in until you find that it's too heavy. Here, I made it all the way up to 300 grams. You'll see that this is the 100 slider, this is the 10s, and this is a 1 slider with all of the other details in it in other pictures. Notice that now it's too heavy, so go back one notch, once again making sure that it is clicked in. This stapler isn't all the way up to 300 grams, but greater than 200, so let's put on the 200 grams and use my 10s. Once again, following the same procedure, clicking over one notch at a time. Looks like whenever I get to the 20 mark, 220 grams, that we're just barely too heavy. The slider or the balance is actually below the level mark. So instead, let's go back one notch. Now I'm at 210, and let's use the fine detailed slider. And let's tap it over till we get to where we're getting close to level. Almost there, maybe a little bit further. Get around in front to make sure you have it all lined up. That looks just about right. And then actually read your balance. This is 210, there's a 9 there, so 219 point down to the hundredths place because the one slider here has tenths of a gram on it. Remember, you can measure down to half of the smallest tick whenever you're dealing with an analog instrument. So this is going to be 219, and getting straight on this, I'd say my slider is closer to the 0.5 than it is to the in between the 0.5 and 0.6, 0.55. So I declare this 219.55 grams.
So now let's look at that actual measurement looking at the sliders. Now you actually should have heard a little mistake on my part there. I said it was closer to the 0.5 than it was to halfway between, but then I declared it to be 0.55. Oops, sorry about that. So anyway, looking at this actually here, I have 210. There's the 9, and then notice there are 10 tick marks between 9 grams and 10 grams, meaning 0.1, 0.2, 0.3, 0.4, 0.5, so forth and so on. And since it's an analog instrument, I can measure down to half of the smallest tick, meaning that if I zoom in maybe a little bit more on that spot right there, notice that I'm declaring this to be closer here to the 0.5 mark than I am actually going to halfway between the 0.5 and the 0.6 mark, which would be the next tick mark over. So whenever I'm actually going to record this measurement here, I would record this measurement as 219.50 grams plus or minus 0.05 grams. And the reason why here is because, looking at this once again, zooming back in maybe, this could have been right here, which I declared is, I'm saying it's right on the 0.5, so 219.5. It could have been at the 0.6, let's say. That would have been 219.6, but I'm allowed to measure with an analog instrument down to half the smallest tick. Halfway between would have been 219.55, and I'm trying to indicate that's not the case, significant figures. I need to actually indicate that it is right on, or at least closer to, the 0.5, so I say 0.50 to point out that it's not halfway between. Now, whenever you do this with a triple beam balance, next picture over here, you actually need to make sure that it's balanced out. So your little tilt guy should be lined up with the 0. The last thing I want to point out is something called parallax error. Now here are pictures similar to the exact same pictures that you saw previously. In fact, these pictures line up perfectly with this picture right here, where I came out with 35.1 centimeters looking straight on. Parallax error occurs whenever you don't actually look straight on. Instead, you look at an angle. Now you're not actually seeing the object right on the line with the tick marks, and since you're looking at an angle, measurements look different. For example, looking from this side, it actually looks like it's less than 35. When we know that it's 35.10, this is saying it's less than 35. Or coming back looking the other way, I might think this is around 37. So make sure whenever you're taking measurements, don't have parallax error, make sure to get right level or right on the measurement, straight on the measurement, not at an angle.